Okay, great. So thank you for having me here. My name is S DaGo, and the work I will present you today is done with the postdoc Jorge Pereda, Sergio Siliberto, and Ludovic Bellon, who are my supervisors. And we will talk about information processing and the cost of information processing and the link between the temperature of the memory and the cost of the erasure. Basically, I will look into three main topics. The first one will be how to build an underdumped 1-bit memory. Then we will look into the cost of a 1-bit erasure reaching the Landau bound. And then we will see a little bit more about what happens for fast erasures. So let's start with the building of an underdumped 1-bit memory. To encode the information, I only need 1 degree of freedom, which can be X, for example, and I will encode state 0, for example, on the left, and state 1 on the right. And to enforce these two states, I need a bistable potential whose energetic barrier is higher than the thermal energy in order to prevent the system from jumping from one well to the other. And of course, this bistable potential has to be tunable, for example, like that, in order to perform the operation. So here you can see the protocol we follow to perform a reset operation. We merge the wells together in order to lose the information, initially in 0 or 1, and then we reset the initial state of the memory with the system always in state 0. This is the reset operation. And in order to get this potential, this bistable tunable potential, we will use an underdumped micromechanical oscillator. So here, for the first time, we will have an underdumped memory and not an overdumped one, because this cantilever is evolving in the air, so at very low damping. The deflection of the extremity of the cantilever will be the variable encoding the information. So here it's the X variable, and we measure this X position through an interferometer system. As you can see on this potential landscape, the system behaves really properly as an harmonic oscillator. And the stiffness of this harmonic oscillator is given by the mechanical properties of the cantilever. And on the spectrum, you can see that indeed it is an underdamped oscillator that resonates around 1.2 kilohertz. So here we are clearly in the underdamped regime with a quality factor around 10. But what I need to provide a memory is to be able to tune the position of the system. So to do so, we will use here the voltage applied between the conductive cantilever and the facing sample. So you can see in the figure here that we are able to tune the center of the quadratic potential, X1, by changing the voltage between the two. So now I can tune the center of the potential, but what I need is a bistable potential. So we have to implement a feedback loop. The principle of this feedback loop is quite simple. We'll just compare the position of the cantilever to a threshold, and whenever I detect the system to cross the threshold, I switch the force. So this is a small video of a simulation of the behavior of the underdamped oscillator. You can see that the oscillator is evolving into one well, and whenever it crosses the threshold X0, I switch the center of the quadratic potential. And in the end, I obtain a very proper virtual biquadratic potential. If you need to be convinced even more, I can show you this experimental measurement of the biquadratic potential that fits really properly the analytical expression you have just written underneath. So here now we have our system and our bistable potential. So here, this is the underdamped 1-bit memory created by feedback. And we will use it to measure the cost of a reset operation. So as you all know, I think here the cost of a 1-bit erasure is bounded by the Landau's bound. Indeed, if you start with two possible states, your information, 0 or 1, and end up with only one, the reset state, which is state 0, you are squeezing, compressing the phase space. And doing so, it comes with an entropic loss. And using the second law of thermodynamics, this entropic loss bounds the average heat required, the average heat released in the environment during the erasure, and also the average work required to erase. And we will reach the equality when we are performing a very slow erasure in the quasi-static regime. The question is now, how about the experimental demonstration using for the first time an underdumped memory and the procedure I showed you for the erasure protocol? So we measured the cost of a reset operation for different speeds. Here on the x-axis, you have the erasure speed, and on the y-axis, the erasure cost. You can see that for very slow operation at small erasure speeds, we are reaching the Landauer bound with a very great accuracy on the work and the heat. But if I want to perform faster erasures, it will require an extra cost. This extra cost was expected to scale as 1 over the duration of the protocol in overdamped studies, but we can see here that this scaling is also matching our results in the underdamped regime. Basically, you can see on this curve that if you want to erase 2 orders of magnitude faster, it will cost you a double price, basically. So these are the measurements, but we wanted to understand exactly what was the cost of fast erasures in an underdamped system. Because it is natural to understand that underdamped memory reduces the cost of fast information processing as it will reduce the dissipative cost. Indeed, if I compare the result I have on the underdamped memory, you can see that we reach the Landauer bound 3 orders of magnitude faster than what was done on overdamped memories. Here, it's experimental results from another team in Lyon. They just did the same, but with colloids into water, so at high damping. And of course, underdamped memory seems more efficient and faster than overdamped one. Because indeed, as I said, it will minimize the dissipative cost of translational motion. You can move the system in the air much faster and with a low price rather than moving a system into water. And if I look at the expression of the dissipative work, it is scaling as 1 over the quality factor. So this is the first explanation of the cost of fast erasure. But something we discovered, yeah, thank you. Something we discovered is that without damping, the memory tends to warm up. I think the analogy with a gas compression can here explain what I mean. If you look at an information erasure, you are compressing the phase space when you merge the 2 wells together, for example, in my protocol. And this is very similar to the compression of a gas, whose volume available would be divided by 2. And if you compress a gas without letting the gas a chance to thermalize with the environment, the gas temperature will increase, right? And exactly the same happens with an underdamped memory. Because there is no damping, there is no way for the system to exchange energy with the bath. The system is isolated. And so its memory will increase, its temperature will increase when I will compress the phase space. And we are able to measure this temperature rise by looking at the kinetic energy. And you can see here in this graph that at the beginning, you are at equilibrium with the bath. So the equiportation holds, you are at T naught. And during the compression of the phase space, the temperature increase and can reach twice the temperature of the bath because the volume is divided by 2. And then there is the thermalization with the surrounding environments and the translational just to recover the state 0. So to put it in a nutshell, during fast erasures, underdamped memories warm up. And this warming has a cost because now the Landauer limit is not kBT anymore. It's kBT effective temperature log of 2. And this effective temperature is linked to this warming effect during the erasure. So thank you for your attention. And again, I hope you get all the points of my presentation: how to create an underdumped 1-bit memory with feedback, how to measure the Landau bound, and a short explanation of what happened for fast erasures in the underdumped regime. Thank you very much.